Welcome and thank you for tuning in. Across Europe, the rail sector is under mounting pressure to modernize, to meet growing passenger expectations, improve resilience, and deliver more digital services without simply replacing entire fleets. We see this reflected in many places. For example, in Deutsche Bahn's S3 program launched in 2024. As part of this multi-year program, DB is not only investing in their infrastructure, but also focusing on digital enhancements of existing trains. Upgrading comfort functions like passenger Wi-Fi, the onboard information system. At the same time, we've seen a shift in their signaling strategy with the lifespan of systems like LZB being extended well beyond the initial plan of 2030, and the broader rollout of the ETCS system pushed out. It's a pragmatic and understandable solution balancing ambition with operational constraints. However, it poses unique challenges on how to extend a legacy system, but already having the future upgrade that is in the pipeline in mind. Examples like these show the real tension many operators face. How do I introduce modern capabilities, digital connectivity, cybersecurity, smart diagnostics, without rebuilding my fleet from scratch? That's exactly what today's talk is about. During the next 10 to 15 minutes, I'll walk you through 3 common pitfalls that derail modernization projects and show how to avoid them, using modular, scalable solutions that are field-proven and rail-compliant. A quick word about me. My name is Alexander von Allmen, and I lead the business line embedded products at duagon. duagon specializes in embedded computing and connectivity platforms that help railway customers modernize reliably, securely, and sustainably. Let's dive into pitfall number 1. The first pitfall is what I call the monolith trap. This is the idea that modernization means a complete system replacement, that we must rip out everything old and replace it with something entirely new. In reality, this is often unnecessary, expensive, and disruptive. Many operators find themselves in this position because off-the-shelf modern platforms lack the interfaces needed to preserve working legacy subsystems. Think about MVB, serial links, or CAN networks. These buses are still functional in many vehicles, but are often left behind because new systems cannot support them. This creates a false choice. Either keep the legacy system and forgo modern functionality like passenger Wi-Fi, AI-driven condition monitoring, or advanced diagnostics, or replace everything, including what doesn't need replacing. What makes this even more painful is that most retrofit solutions are rigid, fixed in form, hard to extend, and costly to adapt later. The result? Projects are delayed, costs balloon, and operators end up with systems that are either over-engineered or under-capable. The solution is modular modernization, and it starts with choosing interoperable building blocks designed for incremental upgrades. This can take the forms of standardized platforms like Compact PCI, which offer rack-based scalable computing architecture. Once a Compact PCI system is installed, you can slot in the functionality you need, whether it's a modern CPU, a Wi-Fi module or cellular module, a cybersecurity component, or a legacy interface. Another possible approach is to split the system to be replaced into individual, more manageable components by, for example, using an off-the-shelf edge computer combined with an external cellular modem or a universal gateway. Rather than replacing an entire system, you scale functionality, not complexity. You keep what works and replace what doesn't. This allows you to manage certifications more efficiently because each building block is independently tested and certified for rail use. You can maintain compliance without repeating expensive requalification every time you upgrade a component. Let's dive into pitfall number 2. The second pitfall is one that is often underestimated or avoided entirely: cybersecurity. Legacy rolling stock was never designed for modern connectivity. The little connectivity that is present is typically based on legacy field buses such as MVB, CAN or serial link with low data rates and limited functionality. The exchange data was strictly for operational purposes and installations were inaccessible behind closed cabinets. But today, we're adding Wi-Fi, remote access, cloud telemetry, live diagnostics, all of which expose the system to new cyber threats it was never built to withstand. The result is modernization introduces new attack surfaces, even in otherwise isolated, safety-certified systems. And it's not just about best practices anymore. Regulations like the Cyber Resilience Act and the Radio Equipment Directive update are coming. Compliance won't be optional. Here's the dilemma. Once cybersecurity enters the picture, many projects grind to a halt. It's seen as too complex, too costly, too hard to apply in any brownfield environment. So either cybersecurity is bolted on late or ignored entirely. And both options are dangerous. The good news is that cybersecurity, even in retrofit scenarios, doesn't have to be overwhelming. The key is to start with the right mindset. Cybersecurity is not a bolt-on, it's part of the architecture. Especially when older systems are being connected for the first time, security needs to be considered early, not left for late. That begins with foundational requirements, things like secure boot, signed firmware, access controls are all features that are now essential for embedded rail platforms. Equally important is the ability to segment critical from non-critical domains. In a typical train, you may need to run safety system alongside passenger Wi-Fi, CCTV or diagnostic. That's possible, but only if the system supports proper isolation, for example through virtual networks, firewalling or physical separation, depending on the safety classification. And then there's the life cycle. A secure system must be maintainable, which means you need a strategy for updates and patching, especially with regulations like the Cyber Resilience Act now taking shape. If I can't update the system securely, it won't stay secure. Ultimately, cybersecurity in mixed fleet isn't just a technical challenge. It's about selecting technologies and partners that understand railway constraints, safety boundaries, and long deployment cycles. If those are respected, retrofit and security can absolutely go hand in hand. Let's move on to the third pitfall, and it's what I call the life cycle mismatch. In the rail industry, our customers, expect hardware to last 15, 20, sometimes even 30 years. That's true for mechanical components, and historically it has been true for many electronic platforms as well. But software doesn't follow the same rules anymore. Today, a typical support window for an operating system is 5 to 7 years. Middleware, security libraries, tool chains evolve even faster, especially when they're based on general purpose technologies that are advancing rapidly to keep up with IT and cloud innovations. This gap creates real problems. You might have a hardware still running flawlessly, but you can't get patches for the operating system, or the tool chain is no longer supported, or your cybersecurity team can't sign off on a platform that hasn't had a security update in 3 years. And when this happens mid-project, or even worse, mid-fleet, you're left scrambling. So yes, lifecycle mismatch is not just an IT nuisance. It becomes a strategic blocker to safe, sustainable system evolution. And unfortunately, this mismatch is becoming more common, not less. As systems become more connected, security demands more frequent updates. As open source software becomes more dominant, the pace of change accelerates. And as mainstream computing platforms evolve, hardware dependencies shift faster than traditional rail timelines expect. Unless you plan for that, you end up with a system that works perfectly on day one, but becomes a liability 5 years later. Let's now look at how to avoid that outcome. To avoid lifecycle mismatch, you need to think about modernization not just in terms of performance, but in terms of durability across both hardware and software. That starts with choosing the right platforms that are architected for long-term support. That means stable, maintainable operating systems with a known support roadmap. It means software stacks that have been validated in rail environments, not just borrowed from fast-moving consumer or cloud ecosystems. But support alone isn't enough. What's just as important is decoupling the system layers so they can evolve independently between the hardware and the operating system, but also between the business logic and the platform it runs on. This separation is what gives you flexibility when you need to upgrade one part without disrupting everything else. It also helps to work with product families that are mechanically and electrically compatible across generations. That way you can adapt and scale without redesigning from scratch. And finally, lifecycle planning doesn't stop at the component level. It also means having processes in place for obsolescence monitoring, redesign paths, and second source strategies, especially for systems that need to stay in service for 15 years or more. When those elements come together, you get a platform that's not just fit for now, but fit for the future. Now let's bring all of these ideas to a real-world example. A customer of ours operating a large legacy fleet across many vehicle types needed to digitally upgrade their train information management system. This includes services like the passenger information service, automated passenger counting, remote diagnostic services, and CCTV. This all had to fit within a certain space in the existing fleet with power constraints and certain lifecycle constraints. Here's what we did. We deployed our modular compact PCI system with a server-grade computing module ready for high data throughput. We ran a modern enterprise-level operating system with a long-term support window that also features virtualization, allowing them to deploy these services within a virtual machine and run them simultaneously but isolated from each other. So you also have the possibility to replace one service or the other, or to introduce even new services. Everything from the passenger info to the video surveillance. The same system was installed across both existing and new builds, reducing training and support complexity. Importantly, the system was built on certified building blocks, pre-aligned with rail standards and future expansion in mind. The outcome is that our customer is able to replace more than 500 units deployed across 3 vehicle types. Additionally, new builds will be equipped with the standardized system at delivery. This is modular modernization in action: scalable, secure, and sustainable. To summarize, avoid monolithic upgrades. Start modular, scale up. Don't ignore cybersecurity. Make it part of your architecture from day one. Plan for lifecycle mismatch. Build systems that can evolve, not just survive. At duagon, we specialize in enabling rail modernization with our embedded platforms, interfaces, gateways, and long-term lifecycle services that bridge the old to the new, reliably and securely. If you're planning a modernization project, whether it's a control system, connectivity in general, or digital services, I invite you to reach out. We'd love to learn more about your challenges and share how we can help. You'll find our contact information on this slide or visit us at duagon.com. Thank you for watching.